Everyone. So today we're going to be starting chapter 12, which is on neutrino physics. Pretty excited about this chapter because I myself are studying neutrinos and all the interesting little bits about them and what you can predict, what you cannot predict. It's actually really neat because the weak force has some very interesting aspect to it where you can do calculations with them, just like in quantum electrodynamics. But then there are other parts that you cannot do calculations on them, or the calculations that you get actually disagree with what the experiment shows. And this has to do with this v minus a, the vector, and then axial, vector minus axial coupling between the in the weak vertices. And the neutrinos are the only one that, only particle we can make really that we can actually do a lot of experiment on and actually probe the standard model in a way that otherwise you would not be able to. So chapter 12 starts off with 12.1, which is a little short section on lepton universality. I'm not going to spend an entire lecture on it, but one thing that I just want to mention is that the evidence for this is because, right, see each of the charged leptons, so the electron, the muon, and the tau, they basically behave the same way except for their mass. That's the only difference between them. Because when you're drawing these vertices for, let's say, a muon, right, decaying into, let's do a decay. Let's go this way then, right, decaying into something else, right? So a W minus, and this will be a muon neutrino, right? You can replace this with a tau, then this will just turn into a tau neutrino. You can replace this with the electron. Technically, the electron doesn't decay because it's the lowest mass version of it, but you could run these diagrams backward so that you can actually have coupling the other way. Okay. One of the evidence for this idea of lepton universality, how basically electrons and muons behave the same way except for their mass. One thing you can look at is actually the tau decay. So a tau, right, we just had that up there, right, can either decay into an electron or a muon, right, and then spits out, let's go this way, right, it decays into a tau neutrino, and then you have a W minus here, and this W can decay into an electron or a muon, right, and then with this corresponding antineutrino, let's put a little comma between them, okay. So this vertex does not actually care whether or not it decays into an electron or a muon, okay. And what you see is that in this type of decay, where you have a tau, right, where the energy, the rest energy, the mass of the tau, is much bigger than both the muon and the electron. Last section we saw that there's some weak decay that depends on the mass of the decay product, because, right, what happened is that you're trying to conserve this V minus A chiral structure, and the particle that has a large mass allows you to have that conservation, where the particle with a very low mass, then basically when chirality and helicity becomes the same thing, then that interactions get suppressed. But the mass of, mass of a tau is about 1.8 GeV. So that's much bigger than the electron or the muon mass. Okay. So both the electron and the muon basically comes out at the speed of light, or the relativistic limits. So there's very little difference between them. Okay. So in this case, you can see that for this first, the muon version, right, is slightly bigger, but actually it's about the same. Okay. And then for the electron version, right, you have basically the same number. They're both going to decay at about 17.5% of the time. The other decay modes is basically this W decays into up and down quarks, so which is the hadronic decay. So so that's relevant, but we don't actually need to concern ourselves with this part. Okay, so so this first section is just the essence of lepton universality. So basically, when we're switching out one charged lepton, electron, muon, or tau, the only thing we're swapping out is basically the mass. Okay, and we can do the same thing with neutrinos. Okay, we can do the same thing with neutrinos. Okay, and therefore the neutrinos actually was treated as the same way because we just thought their masses are all zero. But now we actually found this effect called the neutrino oscillation, where a neutrino actually changes flavor as it travels through space. And in that aspect, what happened is that we're going to see that, oh, it has to have mass in order for that to happen. And we just don't know what the mass is. So this is something that we actually still don't know, the mass of these fundamental particles. Okay, so how do we study neutrinos? So I actually found this neat little video. It's pretty old. Let's see if it opens over here. Okay, hopefully you guys can see that. Okay, so this is actually an experiment that's currently under construction called DUNE. It's called the Deep Underground Neutrino Experiment. And you got a bunch of people there. So the website is just, if you just Google DUNE Fermilab, you'll find it. And the way they make a neutrino beam, there's actually a little video. Hopefully I can play that. Have a beam of protons, which you can make, right? You can accelerate protons as charge. You smash them into this particular target using graphite, and then that makes basically a bunch of ions and neutrons. And then you put these ions into a magnetic field, okay? It's actually called horn. And then by putting it in a magnetic field, you can actually select out a certain charge of ions. And these ions decay and muons, and that out in the last section, right? Mostly decay, about 99.9%. Electrons and muons. So now you're just left with neutrinos. You have a little beam of neutrino that you can actually use to measure things with. Okay, so let's go back to my little sketch artist version of it. Okay, so that's the animation. I'm not sure how, I think it's just some funny music. So let's go through that process just real quick once again. Right, so you have a beam of protons, right, and you're smashing it onto some sort of thin target. Okay, doesn't have to be graphite, but I think that's what they're using right now. Just something with nucleus in it. Okay, and what this does is that the protons will interact with your target, and it will just spew out all sorts of particles. Okay, and a lot of it is going to be pions because, right, these pions are the lightest meson. So therefore, right, you're going to have some neutron coming out, you have some pions coming out. Okay, you have some pi plus. So usually, actually, there's a ratio between the pi plus and the pi minus because you're smashing a proton into things. Okay. Okay. And so now you have just like a bunch of these particles coming out. Okay. What you can do is then you can put these pions, okay, some plus, some minus, right, some neutrons, right, into what's known as a horn. It's actually a curved structure. So I'm going to draw this as a curved structure. Okay. Okay. So if you apply, so you have Let's select for the negative pions in this case. So you have the velocity of all these things going in the same directions, right? So if you want some acceleration in this direction to just make it go in circular mode, right? This is like a little semicircle. Actually gets smaller and smaller as you go. Okay, so the magnetic force is going to be V cross B. So we want V, you want B. So since you have a negative charge, if you want to select for the negative charge, you actually want the magnetic field to point in the opposite direction. So you actually want a magnetic field into the board here. And what that does is that it keeps the negative pions going in the right direction along a circle. Okay. Okay, and the positive pion just hits the wall here. And then the neutrons also hit the wall here. Right. And these horns has to be, I think they switch them out like every 3 months or something like that, because what happened is that this radiation basically just damages the horn, and then you just have a radioactive horn. But then these pions, which you track, you keep in this magnetic field, will go out of the end of the horn as a collimated beam of pions. Okay. Okay. And this horn is probably about maybe like 5 meters long. Okay. Okay. So third, now you have a beam of negative pions, right? Let's say 4 of them, right? They're all going in the same direction. Okay. And what you do is you have a vacuum tube here, basically, and then when you just let the pions fly along, they will decay into muons and neutrinos, muon neutrinos. Okay. And then since these are negative pions, we'll get the negative muons, and then you have the anti-neutrino. Huh. Okay, I should have thought of that. But okay, so now you have an anti-neutrino beam, okay, and a bunch of muons. And what you do is after about maybe 100 meters or so, you smash it into some concrete. The neutrino actually passes through 99.999% of the time, right? While the muon gets stopped by this concrete. Okay. And typically what you have is actually a near detector. So you take this neutrino, you put it through a neutrino detector. Okay, it's just a box. So now you have a beam of neutrinos. And these started off as muon neutrinos, actually anti-muon neutrinos. Okay. And they will interact with yours. They have a very, very small chance of interacting with your target. Typically, the cross-section for neutrinos are in the order of 10 to the minus 40. Okay, much small. 10 to the minus 40. I need to give you the units. 10 to the minus 40 centimeters square. So it has a very small interaction cross-section, but you can detect some of these if you have an intense enough beam. Okay, so this is a near detector, so you can actually measure this. Okay, so the near detector is usually located maybe a few hundred meters or half kilometers from the horn. Okay, and what they do is, let me see, I think they have a better picture up here. Let's see, right? So you have a so you have a near detector right. Oops. Right after, I can scroll back. Right. So this is the proton beam. Okay. And then this is where they smash the thing into a graphene target, and now you have a bunch of pions. Okay, and those pions decay into muons and anti-muons, or mu plus and regular neutrinos. Okay, depending on which one you're selecting. Okay, depending on the magnetic field you're using to select it. And then you have a muon shield that stops all the muons, and now you just have a beam of neutrino coming out, and you actually hit this thing called the near detector. Okay, so it's 300 meters away from the end of the production, the muon, the neutrino production beam, and then you're going to measure basically how many muons you detect per hour, per day, or whatever rate that you want to measure. Okay, and then actually let's talk about the far detector. If I go down, then zoom out, way out. Okay, where now you can even see the curvature of the Earth. So this is your original near detector that we're talking about. Okay, and this neutrino beam is going to travel through the Earth about 1,300 kilometers well, in this case, from Fermilab to South Dakota, and then you have a far detector there. Okay, the reason they're doing this is because the near detector basically kind of gives you, okay, how many neutrinos are coming through here. Okay, and you can actually measure this. And then in the far detector, you make another measurement, and this is actually going to allow us to measure what's known as neutrino oscillation, which is what we're going to talk about later on in the chapter. Okay, so basically, about 1,300 kilometers, not meters, later, right? You have a much more scattered neutrino beam. In this case, the one we made is actually anti-neutrino, and it's actually going to matter, as we'll see in this section. Okay, and this is going to require even a bigger detector in order to measure all these neutrinos that's passing through. And then so in this section, we're going to see how we can actually calculate this interaction cross-section between neutrino and matter and anti-neutrino and matter. Okay, so that's sort of the point of this section in Thomson, which is actually really nicely utilizes all the knowledge that we learned so far in order for us to do this calculation. Okay, so this these cross sections are very tiny, but we can calculate them because it is a weak interaction. Okay, so what's happening is that when you're smashing this, let's say you have this neutrino coming in, anti-neutrinos coming in, right? This target is made of stuff that's made of protons and neutrons, right? And the stuff inside protons and neutrons are made of quarks. Okay, what we're going to do is we're going to calculate basically a neutrino, specifically this muon neutrino. When you do the lepton universality, what's going to happen is that it actually doesn't matter which one it is. You can actually swap this out for another thing. The difference, okay, is that when you have a neutrino come in, so a muon neutrino come in, and it interacts with some nucleus, right, whatever this stuff is. But I think in the case of Dune, it's going to be argon, okay, and you're going to have this charge current exchange, so this W plus in this case, exchange between them, okay, and then it's going to break up this proton or neutron, and then it will just make other stuff with it, okay, but we don't actually care about that part, okay. What happened is that this will actually convert a muon neutrino into a muon, but if this was coming in as a tau neutrino, it'll give you a tau instead. If this was a electron neutrino, it'll give you an electron instead. And the lepton universality allows us to just do one of these calculations and say, okay, they're the same among all the other leptons. Okay, so here's the Feynman diagram. Okay, so in this case, I think what they're doing is they're going to be converting a down quark into an up quark, because this is a W plus, so therefore, right, this has a charge of -1/3, this has a charge of +2/3, so in order, when you add 1 plus 1 charge to -1/3, you get +2/3, okay? All right, so, and then here's the kind of the kinematics diagram, and we're going to utilize that later when we have to plug in the 4 momenta. Okay, well, first of all, the most important thing is to write down the Feynman rules. Okay, the Feynman rules tells us that, well, we're going to follow this vertex backward, right? So this is what's going to give us this U bar P3. You have this weak vertex, right? And then UP1, which is the neutrino, okay? And then you have this coupling factor, the weak coupling constant, okay? And then in this case, since the Q square exchange between them is much smaller than the W mass, and W mass is just massive, right? It's 80 GeV. So So, and then since we're squaring these things, right, the mass of W square, right? So unless the Q square is bigger than 6,400, right, more than 1,000 at least, right, we can approximate that the propagators actually can be simplified as just 1 over, well, the I G mu nu over the mass of the W squared. Okay, and then you have the other side, which is the quark current. Okay, simplifying this a little bit, right, we end up with this piece here and this piece here, right? This is the lepton current. Okay, and this is the quark current. Okay, we're going to simplify this a little bit by just making this lepton current and this the quark current. We're going to see that they're going to be, the calculation for them is going to be very similar to each other because they both couple to this weak vertex. Okay, so since the neutrinos are almost massless, the lepton, we can approximate it to be almost massless also, especially since in the case of the muon. When we deal with tau, you may have to be a little bit more careful because the mass of the tau is 1.8 GeV. But the quarks are definitely almost massless because they're on the order of a couple of MeV. Okay, so we can use the relativistic limit from chapter 4 to calculate these currents. Okay, so this is the equation from chapter 4. I think this is just always going to be useful. I mean, it's on one of the equation sheets on your exam, right? So it's always going to be useful. Looking at this kinematically, right? So we have for particle interaction, okay, we have the neutrino coming in and then scattering off the d quark, and during the scattering, this d quark changes into up quark, and then the neutrino basically turns into a muon. Okay, so what we can do is that we assign the angle, right, the incoming angle here, right, this is going to be 0 for the neutrino, right, and we're going to make the assumption that we can the initial phi angle is 0, and as long as we always make the down quark have the opposite angle, meaning pi, right, we're always going to have we don't lose any generality because, right, we could have picked this one angle because we're going to integrate over all these angles anyway in the future. Okay, so therefore, right, so the down quark is just going to go in the opposite direction as the neutrino because they have to run into each other. Okay, so then, right, we have, so this is 1, this is 2, right, now we have 3. 3 is more complicated because now it's coming out at some angle that we don't know. Okay, the star indicates that we're working in the center of mass frame. Okay, and then whatever the angle of the muon that comes out, the up quark, right, which is this, the momentum 4 here, is going to come out basically pi minus that. Okay, so if we plug these, angles into our little spinor equation, what we end up with is we get 0, 1, 0, -1, and then -1, 0, 1, and then you can go through the rest in order to get the sines and the cosines, right? Because this is going to have this sines and cosine dependence where these don't because you have 0 and pi plugged into it. Okay, and now you do the little dot product. So remember, going back up here, right? This is actually a 4 component, right? Dot a 4 component, right? And when you do the dot, the dot product, you're actually utilizing this G mu nu in order to basically change the spatial component of the one of the vectors into negative. Okay, if you do that, what you end up with is basically you get 4 times the energy squared, and then you just have sine, cosine square, sine square, sine square. Okay, it's really nice. So this basically just comes out to be 2, right? Because cosine square of any angle plus sine of any angle, right, is equal to 1. So you have 2 of those. So you actually just get a factor of 2. This factor of 2 cancels out with this one on the bottom, And then I actually don't like the fact that Thomson does this, but that's what he does, where the Lorentz invariant matrix element just turns out to be, right, the weak coupling constant square, the mass of the W square, times 4 times the energy of each of the particles squared. So this is basically the center of the mass. Sorry, center of mass energy. Okay, and Thomson decides to call this S hat for some reason instead of just S. Okay, I don't see the difference between S and S hat right here. But he's using this notation, so we're going to define that S has actually, the way he defines it is actually 2 times E, the whole thing squared. Okay, because you have two beams you have a neutrino beam coming in and you have a quark beam coming in, right? Each of them will carry an energy of 1 times E, and then when you smash them together, you get twice that, and then when you square it, then you get 4E squared. Okay. Okay, so that's simple enough. Okay, and if we go back to chapter 3 now, seems like we're always using chapter 3 and 4 stuff, right? We plug this into our cross-sectional. So since this is a scattering event, right, we plug this in there, plug it into the differential cross-section for scattering. Okay, what you end up with is basically g to the 4th power, because this gets squared also, and then you have this kind of complicated thing, and then you have the mass of the W times the S, the center of mass still. Okay, what we're going to do is we're going to convert this to G Fermi. G Fermi is equal to this. It actually makes the equation much simpler. So the differential cross-section for a neutrino scattering into a quark, okay, that's going to be basically G Fermi square divided by 4 pi square, okay, and multiplied by the center mass energy, okay, or the center mass energy, center mass energy squared, okay, where the center mass energy is just 4E squared. Okay. All right, since this has no angular dependence, if you were to integrate this, remember that when you integrate over d omega, right, basically you have 4 pi, right? So basically the 4 pi's actually cancel out with the 4 and then one of the factors of pi. So the total cross-section is just G Fermi times the square of the center of mass energy divided by pi. You have a very, very simple equation for neutrino to quark scattering, okay? So one thing to note this, okay, this is different from a lot of the scatterings we've been doing. The neutrino quark interaction actually increases with energy square. Okay, this is actually something different than what we're used to, where cross-section tend to decrease as energy increases, but in the neutrino case, it actually increases. Okay, so well, just to wrap that up, so it's actually easier to detect high energy neutrino versus low energy neutrinos. Okay, so that's one of the caveats that we have to deal with if you're doing experimental neutrino physics. Okay, so now let's do to the flip side. Let's do anti-neutrino quark scattering instead. So the Feynman diagram, right, is a anti-neutrino coming in, okay, and then you have a anti-muon, okay, or mu plus coming out, okay. So you have this particle coming in, and then you have the momentums coming in, and the momentums coming out, okay. You're still scattering this off a quark. These things got swapped back and forth because now you have basically you're going to have a W minus in here instead of a W plus, but everything basically is the same, okay, which is really nice, right? The matrix elements is basically the same. The only difference is that you have these anti-lepton spinors instead, okay, but, right, the weak force cares whether or not it's a particle versus an antiparticle, right? That's the problem. Well, not the problem. This is going to give us a more interesting result. okay, right? Because, right, these 1/2, 1 minus gamma 5 matrices, right, when it acts on particles, it projects out the left-handed chirality part of that spinner. But if you act on this on anti-particles, it projects out the right-handed, right? Whatever the projection operator does, right? It does the opposite thing to particle versus anti-particles. So what's going to happen is that you're going to get the right-handed or the helicity up version of this in the relativistic limit. Okay, so you're going to get this instead. And so we're going to do this in the homework because this is a little bit interesting to do this multiplication, right? Right. So this is basically going to be this GW2 mW squared. You still have this G mu nu, and then you have the current for the antineutrino, right? So let's put that as a mu, and then dot product it with the quark, right? This stays the same, right? While this is right-handed instead of left-handed, okay? And this is going to give us a angular dependence on our matrix element, okay? Specifically this 1/2 times 1 plus cosine theta instead, okay? And then when you plug this matrix element into our cross-sectional calculations, you end up with basically the G Fermi square, 1/16 pi square, but then you have this 1 plus cosine square dependency. So it has an angular dependency when you're scattering antineutrino instead of regular neutrinos, okay? If you integrate this over theta, right, well, actually phi and theta, right, instead of getting just G Fermi square divided by pi, you're going to get this extra factor of 3 on it. It still has this, right, 4 times the energy square dependency, so it still goes up as energy, but it's knocked down basically by a factor of 1/3, right? If you're comparing this to the neutrino scattering, which does not have this 1/3, right, the factor of 1/3 is actually between the antineutrino and the neutrino cross sections. Okay, so when you do experiment, whenever you're have a beam of regular neutrinos, you're going to get 3 times more events versus antineutrinos, which will only get you 1/3 of the regular. And you can see this. Okay, if you go to the PDG, that's the review articles on neutrino cross section. Okay, this is mostly, I think most of the high energy stuff comes from this experiment called NewTev, okay, in 2006. The lower energy stuff, which is also very interesting, right, where you're starting to have this pickup, shows you that, right? So this is about, 0.3 times whatever this, cross section is, right? And then here is like about 0.7, okay, times this cross section. So notice that, this ratio, right, it's like 2.5. It's not quite 3. Okay. What happened is that the particle to nucleon cross section to whatever, right, versus the antineutrino with the nucleon to a mu plus and whatever, right? The ratio of them basically approaches this approximately. What's the ratio between that? It's like 2.5 or something like that. 2.3, right? So it's not exactly a ratio of 3, okay? And this is due to other higher order corrections that we have to deal with, okay? But you can see that, right? This constant, as we increase in energy, we actually end up with this constant ratio between antineutrino and regular neutrino interaction, which is pretty neat. All right, let's wrap that up. So, and then we'll do a little example of how to calculate this in the homework.